Hello everyone. In this video, I want to concentrate on PSPL data interaction using BRAM, and I am trying to show different steps that are required to run in Vivado in order to complete a project in this regard. Before I directly dive into the project steps, in this slide, I want to explain memory support in FPGA and SoC architecture. As you could see, they have been categorized in this slide. For example, we have CLB-based memories, which are the smallest memories that we have on the FPGAs or SoCs, and they are created based on the lookup tables. Then we have block RAM memory, which are different blocks that are distributed throughout the PL part of the SoCs or on FPGAs. In recent FPGAs, for example, UltraScale or UltraScale Plus, we have another type of memory, which are Ultra RAM, and the capacity of these memories are around 8 times higher than the block RAM. In the final, we have composition of memory resources, which based on the design that you have or based on the architecture that you have, you could use the composition of different type of memory that we already have and could access on the FPGA or SoC parts. Based on the explanation I provided in the previous slide, choosing the type of memory in the design process is very important. Depending on the method used, the designer can specify the type of target memory or let the synthesis tool automatically choose the best option. For example, in high-level synthesis-based design, the tool can select the appropriate memory based on the type of data and the access pattern. In the figure below that you could see in this slide, different type of memory that we have are displayed. As I told you, we have CLBs, block RAMs, Ultra RAM, and off-chip memory. And in each of different footnote, you could see the amount of memory that is accessible for each type of memory that we explained in the previous slide. In this slide, the location of different BRAM blocks are shown in the PL. This is the PL part of the SoC architecture. For example, as you could see, we have columns of different block RAMs that are distributed within the PL part of the SoC. In situation where the PS needs to read or send data from the PL, using VRAM as a common buffer would be an effective and cost-effective solution. In this section, in this type of tutorial that we want to explain here, the implementation of a test structure will be described in order to show you if we want to let the PS access the BRAM in the PL part, what should we do? What are the different steps that we should take in order to complete this example? Schematic diagram of this example, as you could see, we have the Zynq CPU block, the AXI BRAM controller, the BRAM part, and the PL BRAM controller. These three are available as different IP cores in Vivado, and you could add it via add IP tool in Vivado. But this one is a custom IP that you should design based on different example and based on your architecture. For example, in this diagram that we have here for this example, I will show you what are the steps to complete this block for this design. From this slide on, I will talk about different steps that you have to do in order to complete the whole project. First of all, you should use the base project, which is Hello World, and then save it as a new project. This hello project, if you are new to the SoC design, I should re-explain it again in short. And it only contains a PS Zynq block. But for this project, because we need to have interrupt, you should also activate the interrupt of the PS Zynq by double clicking on that and going to the setting and configuration of this block. You could add the interrupt to that block. Then the next IP that you have add is AXI BRAM Controller. If you forget about different IPs that are required in this design, you should go back to the previous slide and again recheck the whole schematic that we have for this example. AXI BRAM Controller is the main block that you use it to control the BRAM from the PS side. And as you could see, the IP has the configuration which looks like this one. And if you want to use dual port, you could. There is no need for applying a new change. But if you want to only have just single port, you should go to the configuration and apply changes. As you could see, the inside of the BRAM controller is shown here, and it could be used as a dual port controller or single port controller, which is shown in the second figure. And in this bottom figure, as you could see, the second port of the BRAM should be open because it's just used for controlling the port A of the BRAM. By double-clicking on this AXI BRAM controller, we go directly to the setting of that. And as you could see in this figure, we have AXI protocol setting, which we set it to AXI 4 or left it without changes because by default it is set to AXI 4. And then the data bits to 32, but the only change we will apply is to the part that is required for the number of BRAM interfaces, which in this example, we just want to control the port A of the BRAM from this AXI BRAM controller. So we change this number from 2 to 1, as you could see in this slide. Step is to add BRAM IP, and again, like other IPs, we have to do the setting. For example, by double clicking on this BRAM block, you could see that we have two working modes for this module. First of all, one of them is standalone mode, and another one is BRAM controller mode. Each of these has some advantages and disadvantages and different application. In this example, we choose BRAM controller mode. And also, because in this example, we want to control the BRAM from both AXI BRAM controller and PL BRAM controller, so we use a dual port RAM. So another configuration that you have changed for this example, for this IP, is if it is by default is a single port, you should change it to dual port RAM in order to be able to control it from both AXI BRAM controller and PL BRAM controller. The setup page of this block is shown in this figure. As I told you, the mode has been chosen to BRAM controller, and the memory type is through dual port RAM has been chosen. And in this example, we don't need ECC type or ECC option. So we left the other parts unchanged. In another tab of the setting of the block memory generator IP, which is called other options. You have to uncheck the enable safety circuit. The enable safety circuit is activated to add a special protection circuit to reduce the possibility of data corruption or corruption in the BRAM memory. So in this example, because this example is so simple, we don't need to add this option, and we will uncheck this one. The custom IP that we design here for the PLB-RAM controller has a FSM, a finite state machine, which looks like the diagram that is shown in this slide. It starts from the idle states, and based on the start signal status, it will go to the next state, which is read RAM, and again it looks to another signal which is read down, and whenever it become 0, it will continue to do to stay in this state and continue reading the data from the BRAM, and until the signal which is called read down will be 1, and it will go to the next state, which is read end, and then after this read end state, it will go to the next state, which is a write RAM, and then based on the write down, which it make another decision, it will go to the another state, which is write end, and finally it will return to the first state, which is idle. There are different steps that you have to follow in order to create a custom IP for the PLB-RAM controller. They are very similar to creating a custom IP for any other module that you have. For this goal, you have to go to the menu, which is called Tools, in the toolbar, and then choose the Create and Package a new IP. And in the page that will be pop up, you have to choose Create a new AXI peripheral, because this PLB-RAM controller that you are going to build in this design have to be able to communicate with the AXI bus. So between different options that you already have in this create and package new IP form, you should use the last one, which is used for creating AXI peripheral, AXI compatible IP, I mean. Next step of creating this IP, you have to choose a name for that. In here, in this example, we have chosen PLB-RAM control, and I will choose another description for that PLB-RAM controller, and the version is also optional for you. You could choose. This is the default number, but you could change it if you like. Two different new codes will be generated after you completed all the steps for creating an AXI peripheral IP. One of them has the index of S00. As you could see, this is the name that you have chosen for this IP, and this one is the version that you have chosen, and this one is the index that will be added by the software. And as you could see, the type of the file that has been generated by the tool is Verilog, but it is totally dependent on the default setting that you apply whenever you start creating the project. For example, in this project, we didn't change the default setting, and by default it will generate Verilog. But if you are familiar with the VHDL coding, it is better to change it at the start of generating the project. But there are some changes that you have applied to these two codes that will be generated by the tool. First of all, you have to add the instantiation of your IP or your special module that you already have written for the PL BRAM controller. And this module that until now I haven't explained about it should be written in a Verilog, and it should be contained and that FSM that I already explained it in the previous slide. And as you could see in this S00 Verilog code, we will have a place which is highlighted with add user logic here, and in this part you have to instantiate the RAM read write module that you already written, the FSM code I mean. And then you have to port map them with the input output different IO ports of that module and the new name or ports of the topper module, which here is S00 AXI. Another module, which is the top module between these three, has this very similar name like the S00 module that I already explained, but it doesn't contain that index. It is just PL BRAM controller and the version number that you defined in the name. These changes and these changes also should be applied in both of these files, which are adding different IO ports that are defined in the main module and the sub module, because in different IP creation we have a special module that we want to make it IP and use it with other IPs. So based on the example that you have, the IO ports could be changed, and all these IO ports should be recognized by the top module. And for this regard, we use the definition and the definition of this input-output ports here in our code, in both of these codes. Another change that should be applied is whenever you are instantiating the S00 module, which is the sub-module of this module, again, all those IO ports that you already defined should be also added here, and then port map them between the new name or the new signals that are defined in the topest module, which is PL BRAM controller version 1. Applying all these changes to these two generated module by the tools, the next step is to package the IP. If you go to the Flow Navigator and choose the package IP, the menu like this will be appeared. As you could see, these are different steps that should be completed to have a complete IP package. And after applying all these parts to be checked, you could do the repackage IP, and this is the final step for packaging. But some of the time you have to apply some changes. For example, as you could see, some parts are not green checked here, and you should click on each of them and see if the warning could be ignored. You could go to the next step, but otherwise you have to be curious about different warning that is generated here and doesn't let it to be green checked. In the next step, we want to add an interface to our design. For example, we want to add all these or to group all these R data, W data, or enable or write enable or address of the main module to adjust a new interface And because of that, we will go to first to port and interface part, and then choose the add bus interface. And to the new for the new page that will be pop up, you should type BRA, the first alphabet of the BRAM RTL interface. And by choosing this interface, as you could see, different signals that we already want to pack, and they are related to the BRAM module or BRAM IP controller will be appeared here. You will OK this one, and you will go to the next step of adding this interface. You will in the general tab, you will choose the name for that. For example, here we have chosen BRAM port, and then in the second tab, which is port mapping, you should apply port mapping between your module and the equivalent this one is the equivalent interface port name, and this one are equivalent IPs port name. So you should choose, for example, reset with reset here, and port map them together, enable here and enable here, and D out or R data, or for example D in to the porting to the W data. And by doing all the port mapping, this step will be completed. And if you confirm this page, the BRAM interface with the name of BRAM port and with the port mapping that you already apply will be completed. And as you could see in the package IP menu, in the ports and interface, you could see that all those ports have been packaged in just one port with the name of BRAM port, and which is very useful in the design. Whenever, for example, you want to connect this port to another port of the BRAM, which both of them are bus type with the BRAM RTL type, it is very helpful for you in order instead of connecting each of these ports together in the final block design, you just need to connect the this BRAM port, for example, to the port A or B of the BRAM module, the main module. If you like to have your IP or use your IP in your design, the last step that you should do or follow is to go to the setting and then go to the IP repository and add the address of the IP that you already designed to your project. For example, here the address of the IP that we already designed is in the Vivado project book 2 and the blah blah. In this project, in order to observe different signals at runtime, we want to add a logic analyzer. ILA is the abbreviation for Integrated Logic Analyzer, and it is a block that we could use it to observe or monitor different signals of the design. For example, in this design, we want to observe the interrupt of the, for example, PL BRAM control that we already designed, and also the BRAM port of the PL BRAM control again. And for adding this IP, you have to right click on the signal that is connected to that port and then choose the debug. By choosing this option, after doing the run connection automation, this ILA block will be automatically added to the design. The completed block diagram of this design is shown in this figure. As you could see, the first block was Zynq PS with interrupt port has been enabled, and then another block was, the second block was AXI BRAM Controller, which we choose just one port for that in the setting. And the third one was the block memory generator that we have here. And again, if you could remember, we choose dual port BRAM, and the last block was PL BRAM controller. That's, as I told you, we have designed it with running different steps of IP creation as a custom IP in the Vivado. Another blocks have been also added to the design, which are just added for after running block automation. This one is processor system reset. Another one is AXI Smart Connect that is used for connecting the master of this to the a slave of these two blocks. And for example, if you want to do the addressing, or if you have for example, number of bits incompatibility with this smart connect, all this will be solved. And this one is the last block, which is I explained it before, and after again running block automation, or sorry, connection automation, this block has been generated, and it is an integrated logic analyzer, and it is used for monitoring the different signals that are the input of this, for example, the interrupt and BRAM port. After completing the design in the diagram tab, you have to go to the address editor tab, and then based on your design, you could choose different ranges for the addresses. For example, for the PL BRAM control and for the AXI BRAM control. Here in this example, both has been chosen as 4K. After completing the block design and then running the create HDL wrapper and generate bit stream, and finally exporting the hardware and launching the SDK or Vitis. For example, here we have used the Vivado 2018 version 2. Because of that, we have SDK here in this Vivado tool. What if you use the newest version after 2019? You don't have SDK anymore, and you will encounter the Vitis environment, which the environment is very similar to SDK. If you are familiar with SDK, changing or mitigating from SDK to Vitis is not a big challenge for you. Don't worry about that. We have to run different steps here in order to complete a project. First of all, we have to run for creating a board support package. I omit all these parts because I imagine that everybody that are listening to my to this video is a little familiar with doing the project in Vivado and SDK. So I'm just explain it in very short and brief. You know that first of all, in the SDK environment, you have to create a board support package, and then go and create another application project, and link this application project to the previous board support package that you already created. And in the application project, whenever you are creating that one, you could choose between different templates that are available in SDK. For example, Hello World is the simplest and basic design that you could edit. But if you don't like to add those, you could run the empty application or empty project, and then by right-clicking on the src folder, you could generate the main.c, the main code that you have, add all the library that has been created after launching from the Vivado to the CK, or different library file that you already want to generate in this environment. But here in this flowchart that we have here, all the steps, all the codes that should be written and included in your main.c file has been explained in detail. For example, you should have a part which writes BRAM data via BRAM AXI controller, inform the PL controller to read the BRAM data. The PL controller reads the data internally and write in the same position. The initial data is modified by the CPU, is notified by the CPU, sorry. And then enable the write end signal after writing is finished, setting up the GPIO interrupt, and finally the BRAM data reading interrupts, and all the print will be displayed. In the next slides, I will explain the main.c code in brief. For example, we will have a while loop, and in that while loop we will check the interrupt flag with the if instruction, and then if it is 0, it means that we will at the start of the running the code. So it will ask you the start address, and then you have to provide the start address value, and then it will retype it again for you that the start address is the value that you have provided here for the SDK. And then it will ask you to provide the links, and then you have to provide it, and then it will again print the value. After that, it will call another function which is called BRAM read write, that I will explain it in the next slide, and the value of that will be assigned to the status parameters that has been defined at the start of the main.c code. It's obvious. So it will check if a status is opposite of is success. It means that this BRAM read write couldn't be completed, or maybe it will cause an error. So it will print on the console that BRAM test failed, and the interrupt flag will be 1, and then it will go again to the first part and start to ask you the new value for the start address and the links. Coding in the CK, we will go to the BRAM read write function, which is the main function of the main.c code. In this code, first the data is written by the BRAM controller. The initial data will be set by the test start value parameter, and then in this if function we will check if start address plus links is in the range of BRAM address or not. If it is outside of the BRAM address, and then the excessive failure will be returned for this function, and then it will go to the first of the main.c and again ask the new value for the start and links, the start address and links, and then it will go to the for loop in this for loop by different step that is defined in this based on the start address and lengths and BRAM byte number, which is another parameter that is set in this main function. The X BRAM write register will be called, which is a function that has been defined after creating different driver and exporting from Vivado to the CK. As you could see, it has three parameters. The first parameter is base address, which is defined in xparameters.h again, and I, which is the value that has been changed in this for loop. It means that the right data will in each running this for loop will be written to the address of base address plus I, and then this write data will be increased in the next step. In other parts of this BRAM read write function, by using the PL-BRAM control mWrite, the different value that are required for this IP will be set and rewritten in different address, which are, for example, the offset of RAM lengths from the base address, or the offset of address again from the base address, initial data from the base address, and control from the base address. Completing the SDK main.c code, we will go to the run configuration in order to do different configuration for programming the SoC and then running the code on this SoC and checking the result. One of the settings that you have to apply is in the target setup. You should choose reset entire system and then check all these parts: program FPGA, run PS7 initialization, and run PS7 post configuration. If you go back to Vivado environment and in the hardware manager, you have to choose to connect to the device that you already want to run the test on that. After that, you will have an option of seeing the waveform for the ILA, and as you could see, this window, which is for the waveform of the ILA, will be opened. And if you go back to the SDK environment, you could see that it is waiting for you to provide different value for the start address and the lengths. For example, here I have entered 0 for the start address, and it will, as we see in the C code that we already written, the start address will be again retype here, reprint here, and the value will be shown. And then it will ask you for the length, and the number 10 will be provided in this example, and then it will print some result that the address start is 0, and it will continue until 9, which in total they are 10, as we provide the number 10 for that. Again, you have to go back to the Vivado environment. Finally, you could see the final result in the Vivado environment. By applying zoom in or zoom out, you could exchange the clarification of the waveform, and as you could see, whatever has been provided to the BRAM in the D-in, it will be shown in the D-out after one cycle differences, for example 1 to 10 and then 1 to 10, and this is the final result. But in these waveforms, as I told you, it could be generated or could be monitored because of adding that ILA that we explained in the slide. This is the final result of the example, and this is the final